Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome back to the Deep Dive. Today, we're taking a fascinating and I think often overlooked detour into the architecture that basically defines our digital lives. We're talking about computer networks. So if you're looking for the essential concepts, the functional roles, and the surprising trade-offs that govern how data moves from point A to point B, this deep dive is absolutely your shortcut.
That's right. And we're not just, reading definitions today. We are going to quickly synthesize the core knowledge around how these interconnected systems, whether they're linked by a physical cable or entirely wirelessly, actually manage to communicate reliably.
Our mission is pretty simple. We are going to break down the key hardware components, understand the crucial set of rules, the protocols they follow, and discover why investing in this architecture is both, well, essential and inherently risky. So let's just jump straight into it.
Let's do it. Let's start with the traffic managers. When you look at any functioning network, you have two primary categories of hardware that dictate how information flows. You've got the internal controllers and the external dispatchers.
Okay, let's unpack this. If I'm setting up a network inside just one building, say a campus or a small office, and I want all of the devices to talk to each other, maybe share the same printer, what's the core controller there?
That is the switch. Think of the switch as the traffic cop for the local area network. Its function is to connect all those local devices, your PCs, your servers, your printers.
Okay.
By linking everything together, the switch manages the conversation within that confined space, and it enables that vital resource sharing, which is, the whole point of a local network. It reduces your costs.
And crucially, the switch operates at the data link layer, which is layer 2. But that local conversation doesn't help me email someone across the country. And here's where it gets really interesting. How do we connect my local network, managed by the switch, to the massive external network, to the internet?
That's the job of the router. The router is the network's global dispatcher. It operates at layer 3. Its purpose is to connect multiple networks together, your home network to your neighbors, your corporate network to the internet itself.
So it's the decision maker.
It's the decision maker, exactly. When data hits the router, it analyzes the destination address, and it selects the best possible route through all the different connections and pathways available.
Okay, so if the switch is the local traffic cop and the router is the global decision maker, we need to talk about the devices actually, sending and receiving data on that network. This defines that fundamental relationship between the server and the client.
Right, and the server is the engine of the network. These are powerful computers that specialize in holding and providing resources. So we're talking shared files, databases, programs, and the network operating system.
They're the providers.
They're the providers of centralized access.
Which means the clients are the consumers. So your laptop, my phone, our desktops, we're sending requests to the server and accessing those network resources.
Exactly. It's a foundational request and response relationship. It's built entirely on that principle of sharing resources.
Okay, so now we know who is routing the data. Let's pivot to the physical highways the data actually travels on, the connectors and traffic managers themselves.
We're talking about transmission media.
Right. These are the actual physical carriers, the links, the channels, the lines that interconnect all the hardware. And it's not just one type of cable, is it?
No, not at all. You still see older coaxial cable sometimes, but primarily today we deal with twisted pair wire, which is like your standard Ethernet, and then the far more robust optical fiber cable.
And there's a trade-off there.
A huge architectural trade-off. Fiber gives you vastly higher speeds and less degradation over distance, but it is expensive to install. Twisted pair is cheaper, but it limits your speed and distance.
And for most local connections, we're talking about a LAN cable, an Ethernet cable. But what's managing the flow of information out of my specific computer and onto that cable?
That crucial interface is the network interface card, or NIC. Every single device that talks on a network has to have one. The NIC is the gatekeeper.
The gatekeeper.
Yeah. It sends and receives data, and most importantly, it controls the data flow between the actual computer and the physical network media.
And for all of our devices, without wires, the phones, the tablets, we're relying on access points.
The access point is the bridge. It lets devices connect to the network entirely wirelessly, and that flexibility is, well, it's non-negotiable for modern networks. You have to have mobility.
Yeah. Before we leave the physical hardware, we really should clarify a common point of confusion: the difference between a switch and a hub. We said the switch is intelligent, it's targeted, but what exactly does a hub do?
The hub is basically its historical predecessor, and it's very inefficient. If a device sends a request to a hub, the hub just acts like a simple distribution center. It takes that signal and it transmits it to the entire network.
Oh, wow.
Yeah, it splits the connection to every single connected device. It's like shouting a message across a crowded room and just hoping the right person hears it.
Whereas a switch, it reads the address and sends it only to the intended recipient.
Precise.
That distinction shouting versus a targeted whisper, that's a great way to understand network efficiency. So now let's move beyond the physical parts and into the network's intelligence. The rules, the addressing, all the systems that govern communication.
Right, because the hardware can't communicate without a universal language. And that language is defined by protocols. A protocol is simply the predefined set of rules that enables any two machines to exchange data across the network, reliably.
And we hear terms like TCP, IP, UDP thrown around all the time. What is the fundamental distinction the listener needs to understand between, say, TCP and UDP?
This is a massive architectural trade-off. TCP, the transmission control protocol, is connection-oriented. It guarantees delivery.
Okay.
It ensures packets arrive in order, and it even asks for retransmission if something is missed. It's like sending certified mail. It might be a little slower, but it's reliable.
So you'd use that for email or banking, things where data integrity is everything.
Exactly. Then you have UDP, the user datagram protocol. It's connectionless. It doesn't guarantee delivery or order, but it is incredibly fast.
And that's the choice when speed is more important than perfect reliability.
Right. Think of streaming video or online gaming. If you miss a frame, the application just keeps going. You're sacrificing that reliability for low latency.
And to make sure that protocols from different companies can all communicate, there has to be a common blueprint. That's where the OSI model comes in, right?
Exactly. The Open Systems Interconnection model isn't software, it's a conceptual reference framework. It specifies 7 layers of standards that must be followed for communications.
And its utility is that it lets developers focus on one thing at a time.
It's profound. It allows a developer to focus on building a robust function at, say, the application layer, and be confident that the standards below it, like routing at layer 3, will just handle the transport seamlessly.
This all works because every packet of data has to know where it's going. With billions of devices talking at once, how does the network know the precise destination? This is managed by, multiple layers of unique identifiers.
We have 3 essential identifiers. First, every device has a human-friendly hostname, its unique name. Second, for global routing, we rely on the IP address, the Internet Protocol address.
That's the device's logical map location on the internet.
That's right. And we started with the standard 32-bit IP addresses, IPv4, but we ran out pretty quickly.
Right.
That's why the shift to IPv6 is so essential. It uses a massive 128-bit address space, which allows for trillions upon trillions of unique identifiers. It's safeguarding the future expansion of the internet.
So the IP address tells the router the general location, the city, so to speak. But that's not enough. Every device also has a physical identity.
That's the MAC address, the Media Access Control address. This is often called the physical address because it's burned onto the network interface card by the manufacturer. It's a permanent 48-bit identifier.
So the IP address is the city, the MAC address is the specific street address.
That's a great analogy. The IP address tells the router where to go in the world. The MAC address tells the switch who to talk to on the local network.
But we, as humans, we use words, not numbers, to find websites. So that's where the DNS server performs its magic.
The domain name system server is, it's one of the most critical ports of the internet's infrastructure. It is the phone book of the internet.
Yeah.
It takes that human-readable web address, like thedeepdive.com and translates it into the corresponding numerical IP address that routers need to do their job. And it's a massive global system of servers all working to keep that map updated.
So once a packet reaches the correct device, the right IP address, the job still isn't done. That device might be running a web server, an email client, and a game all at once. How does the data get to the right program?
That is handled by the port. A port is a logical channel that identifies the specific application running on the host device. So for example, web traffic usually goes to port 80 or 443, while email might use port 25. The port number makes sure the package is delivered to the right program.
And finally, the essential glue that binds this whole system together, making sure the IP and the Amex address can communicate locally, is the Address Resolution Protocol.
This is absolutely fundamental. ARP, the Address Resolution Protocol, takes the logical IP address and converts it into the physical MAC address. If my computer wants to talk to a printer on my local network, it uses ARP to find the printer's physical hardware address.
There's a reverse of that, too.
Correct. RARP, or reverse ARP, does the opposite. It gives you the IP address when you give the physical address. The entire reliability of local data transfer relies on this constant, invisible conversion.
So why did we build this complex, multi-layered system? Let's move into our final section and look at the practical utility. What are the common benefits of this architecture for, say, a modern organization?
Well, the utility really boils down to efficiency and shared access. Resource sharing printers, scanners, databases sharing expensive specialized software licenses among many users.
And providing fast, effective communication and data exchange.
Absolutely. When you synthesize those advantages, it's clear that electronic communication over a robust network is just vastly more efficient and less expensive than trying to operate a business without one.
Because you can share those expensive physical and digital resources.
Precisely. However, and this is a big however, this amazing complexity comes with serious trade-offs. And when we connect this to the bigger picture, the required cost and the ongoing risk factors are critical considerations.
What's the #1 architectural drawback that organizations have to contend with?
Security risk, without a doubt. Connection means vulnerability. Your data is exposed if proper security precautions aren't taken.
So implementing robust security like file encryption, strong authentication, firewalls, that's not optional. It's a necessary architectural layer.
It's mandatory to mitigate the sheer risk of being interconnected.
And beyond security, there's just the cost and maintenance to keep the system running.
The initial investment for hardware, cable installation, sophisticated software, it's significant. But the ongoing maintenance is often overlooked. Networks need constant administration time, and components fail.
All the time.
Constantly. We're talking about frequent server failure, cable faults, components becoming obsolete and needing expensive replacement. It is a constant battle against entropy.
That brings us to the close of our dive. We've traveled the entire architecture, from the physical media to the intelligent dispatchers like the router, and finally, to the unique identifiers that ensure targeted communication.
We cover the importance of protocols, contrasting the reliability of TCP with the speed of UDP. But I think our deepest takeaway today has to be about that invisible infrastructure.
You're talking about the foundation of the network, the Address Resolution Protocol, ARP. It's always linking that abstract logical IP address, the device's address on the map, to the fixed physical MOC address, the device's ID on the ground.
Just consider the sheer, staggering volume of times that conversion has to happen every single second across all the local networks of the global internet just to successfully route one packet of data. This nonstop, high-speed translation is the foundation of modern network reliability.
And that constant need for physical identity confirmation, it raises an important question for you to think about. Given our deep reliance on fixed physical MSC addresses for local routing, what inherent limits does this impose on the future? On things like network identity management and next-generation security? It's a critical challenge that's built right into the very bones of the system.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo, haven't you checked out our new book yet? Link in description.